Hey everybody, thanks so much for allowing me to be here today to talk to you all about our work at plastics.com, focused on using artificial intelligence to power resin selection and procurement. What we're really focused on, though, is design engineers and procurement professionals. We really help them to enable them to design innovative products, from starships to medical devices that save lives, to food packaging that helps people in Africa get clean water. And I think that's really important to remember what plastics enable within this world. And so we're at plastics.com focused on providing the right resin right now for those very innovative products. As a brief history, I didn't start in plastics. I actually started another company and exited that a few years ago, and I have a PhD from MIT. But I spent the last year focused on traveling the world, visiting different plastic manufacturing facilities with Techno-Apex and Biologics, and met a lot of really interesting people along the way, as well as the CTO of Techno-Apex, Mike Roberts, who was very gracious in providing me a lot of donuts, as I got to know a lot of information about plastics manufacturing, the sourcing process, what the products plastics are used in. In April, I launched plastics.com with John Zessin, who's the chairman of the board. He's a plastics expert, built numerous plastic companies within distribution and production of plastics, most recently at M. Holland. And together we started plastics.com, and we're really focused on building AI tools to enable design engineers and procurement professionals to find the right plastic right now. Over the last 5 months, we've hired 16 people in order to help us develop the technology and start to make a lot of progress in making it simpler to find the right resin. So I get a lot of questions around what is Herman Ai. Well, Herman Ai is our AI framework that helps engineers and business owners with technical engineering questions in plastic procurement problems. And Herman Ai is built into plastics.com. And so plastics.com is this marketplace that is coupled to Herman Ai that allows us to help engineers navigate the extremely complex plastics industry. I mean, plastics are literally the most advanced materials in the world, and they should be in more products, in my opinion. And so why are AI tools today struggling to solve the complex engineering problems? As the last speaker noted, they tend to hallucinate. They have overly general or simplistic answers for very complex engineering problems. They have been trained on outdated or biased information, which limits their utility for sort of today's problems in sustainability, recycling, and enabling next generation materials that are currently being developed to be found and suggested by these LLM models. And it also just lacks technical knowledge, transparency, and is trained on the wonderful internet. And the wonderful internet has a lot of opinions, tends to be pretty biased, and really that is why these LLM models tend to fail. But if you dig a little deeper, the frontier models fail because they're not trained on physical information. Engineering, physics, they're all equation-based. Natural language models tend to be language-based. They're trained on Stephen King's novels, not necessarily, a high school physics book. And that really limits their ability to understand numerical reasoning, do simple things like unit conversion, and even limits their ability to do precise property predictions or even have validated predictions coming from those models. And so the frontier models are really falling short for providing high quality information to engineers designing the best products in the world. And so to understand really where these AI algorithms fall short, we have to start by understanding what an LLM is. And just let me break this down for you. It's a little complicated, but it starts with a user query, sort of like machine learning is. And then all it is really doing is trying to predict that next word. It does that through tokenization, which is really just saying this word is made up of these, letters in the alphabet. What matches in the world that I've seen before the next word. And then it goes into this foundation model, which does some embeddings and some complex math, and then comes up with, the user response. In this case, I would like it to be fun. If any other, thing would be wrong. And if we go even a little bit deeper, so after you've gone through the transformation of the input query to the user response, you'll see that these LLM models are really made up of just like these big tensors that have a lot of weights and biases. And these tensors are actually trained or sort of developed by using just general knowledge from like books and novels and internet sources. And so it's really good at general intelligence. And what I mean by that is it has this ability to understand a very simple query like, machine learning is fun, but it really struggles when you put numbers in front of it, if you try to get it to do advanced things like vision. And what we're doing at Plastic AI is trying to overcome the limitations that exist within current foundation models and deliver a better user experience for plastic engineers across the world. And so how are we doing this? We're taking a fundamentally new approach in order to build Herman AI. And this starts with how we're getting all of the data for our product. It starts off by caching the internet like everybody else. However, we're then extracting the high quality open source data sheets that the plastics industry already has released to the world. We also are pulling in books and expert knowledge. And then we're using that information to build the next layer on top of that, which is an ontology. An ontology is just a fancy way of saying, how are we going to categorize all of the properties and knowledge within the specific plastic industry. And then we can build up machine learning models, like precise machine learning models that understand the physical world, that are very good at numbers, and start to fill in all of the different gaps within the plastics industry in order to build a better model of the data within the plastics industry. So sort of like an augmented model. And that is like highly accurate. And I'll show you that in a few seconds. And then we build plastic similarity, we build knowledge graphs, we do a bunch of math, and we make this entire space of plastics information highly searchable. And we're doing this in conjunction with producers and distributors and other design firms within the field in order to provide the most knowledge, be that real centerpiece of community within the plastics industry. And then we get to the LLMs. And our approach to using LLMs is to build what's known as an agentic framework. And that means that we use different LLMs that are trained on particular tasks. And then we have an orchestration layer that allows us to sort of weave those different agents together in order to deliver the best engineering chat experience that exists with any engineering domain. And that is Herman AI. So we didn't start with this entire ontology. What we did is we took a fundamentals approach and we built it up one layer at a time. That simply started with plastics data sheets. We built data extraction algorithms using traditional OCR techniques augmented by LLMs. We built out plastic ontologies to over 180 different types of numerical properties and 350 different categorical properties that are associated with each one of the plastics that can be made by many of the manufacturers here at this show. And then we structure that information, we do unit conversion and normalization of that information, and then we fill in the blanks with our property prediction. And that makes a highly searchable data set that LLMs can then start to leverage. From here, we're kind of surprised that we've gone through all this work and we were still seeing a tremendous data sparsity problem. 80% of numerical properties only are represented in 5% of all plastics that we've categorized so far. So that means out of the 197 properties that we have, about only 40 properties are routinely accessible on any given plastic. So what we've started to do is build high accuracy machine learning models that are physics-based models that allow us to predict those properties. And so a lot of people ask us, how good are those predictions? Well, they're better than nothing, is what I usually tell them. But really, what we have in the plastics industry is this idea of a baseline model, which is taking a base polymer family and then comparing your polymer against that base polymer's mean average, and that is, fairly representative. And they're not wrong. That's like a good starting point in the absence of a more advanced model. And what we've done is we've produced that model, and we've been able to get an R-squared value of 94% versus an R-squared baseline value of 55%. So that ultimately reduces the error in our predictions as compared to the current best practice in the plastics industry by about 70%. And so we've used these models to actually enrich our data to date, doubling the number of searchable properties within our data set. We currently, by the end of the year, are going to probably double that again. And then in 2026, we are focused on 10xing the amount of data that is currently searchable within our data pipeline. From there, we go ahead and we make sort of knowledge graphs or do similarity scoring across all the different plastics. So when people come to our website, they have the ability to search our platform by application or whatever they're interested in, and then find clusters of plastics that suit the need of their innovative product. And how are we doing compared to baseline LLM models? Well, if you look at OpenAI's ChatGPT 5 model, in a head-to-head comparison with our most advanced model, we outperformed their model by about 50% of correct answers versus their, we get 83%, which is 50% roughly better than the OpenAI's most recently released model. And the interesting thing to note is that in our evaluation set, we've run this now multiple times across many different models, and OpenAI's 4.0 model was the best performing model that we ever tested for getting plastic properties right. And what you'll notice is that model has actually been deprecated by OpenAI because engineering is not a core source of revenue for them because of the other issues like hallucinations, providing not very good answers, and it's actually been deprioritized. So their models are actually getting worse for helping design engineers develop some of the most innovative products in the world. And so we're really trying to help produce better models for engineers where OpenAI is actually moving away from those engineers. And so if we put it all together, Herman Ai is really an intelligent, dynamic search platform. It's no different than, kind of like Google search on steroids, kind of like Gemini. And really what we're focused on doing is making it fast, transparent, so people know where the data comes from that's inside the model, and making it secure. We are not using OpenAI. We're just not like a OpenAI wrapper. Herman is a privately hosted LLM. It's not built on cloud-based frontier models, and it is really secure so that we can work with the most innovative products in the world, and people feel safe talking to Herman. And so the way that our agentic system works is a user query goes in, we do this orchestration, we do a number of different types of steps to build a workflow. From that workflow, we pull in all this information, we summarize it, we do an evaluation to make sure it doesn't violate the laws of physics. We then make sure that it's not sending out anything that's dangerous, and we do all this within 15 seconds. By the end of Q1, we should be about half of that time for providing highly transparent information, but we'll also be searching 10 times more information in that time period too. So we anticipate about 10xing the quality of answers in the next 4 or 5 months. And so, is that enough? And we just don't think fancy search is enough. Because engineers need more than fancy search. They need to understand pricing, value chain risks, and lead times. And so that's where Plastic AI comes in. It is really this generative engineering marketplace that leverages our AI tools in order to provide more intelligence, transparency, and protection to people looking for plastics. And we think that it's really important that this intelligence allows you to own your own data so that you're not at risk of having IP leakage while you're leveraging some of the most frontier models in production. And so why is this important? And why is this needed? It's really needed because the materials market within plastics is just so complicated. Plastics as a material class are really the most advanced materials in the world. And we need to bring speed and connectivity across the value chain. And that's because the data that's needed to do material selection, compounding, logistics, conversion, and engineering simulations all right now sits in data silos. And so what we are doing at Plastics AI, or plastics.com, is really bringing all of that information together and making it accessible in one place. So where do we fit in? In already a fairly crowded market. There's hundreds of vendors here, thousands at K-Show a couple of weeks ago. And the way that we fit in is that we are really just a software layer that's connecting the engineers, the distributors, and compounders faster than ever before, providing more information to those people, and making the ordering process more simple. So our marketplace is really just powered by a proprietary knowledge layer. From expert plastic knowledge, machine learning predictions, transportation management, inventory and lead time, we take all of this, we put it through our generative AI tools. I just told you about how they work. And we develop unique and novel user experiences on top of that. From plastics experts to pricing engine to order management and supplier management. So it's really this entire ecosystem of tools built on a common sort of data infrastructure, which we think is the future of plastics. And the reason for this is because we aim to minimize the time to value for engineers. This is important if you're going up against, this is important if you're going up against a metal to plastic replacement part, or if you're trying to help a brand find more sustainable parts. There's a lot of applications where speed to lead is really important. And that is because you have the ability to do material selection, do rapid sampling, material qualification, all leveraging Herman Ai. And we're not doing this alone. We're doing this in conjunction with producers and distributors. And this has just been a really rewarding experience for us. And now we're just getting to the point of rolling out rapid quoting and order tracking. We launched this platform at K-Show just a few weeks ago. We're up to, basically the max number of early access members that we want. But every one of our early access members has the ability to see unbiased resin data, use powerful analytics tools, and collaborate on projects with their own internal engineering teams. So we really are the first intelligent marketplace. We would invite the sort of merchants or suppliers or design engineers in the room to really join or consider joining our merchant portal so that you can access these design engineers, manage your products on a premier category-defining domain, and really help engineers within the American economy and the global economy find the right plastic right now. And so if you'd like to join us, we would appreciate you signing up as an early access member. You can go to this link, and then you can scan your badge, and you can create an account. Thank you.
Okay, brilliant. Thank you so much, Dave. That was a very interesting talk. Nice breakdown of how AI models actually function behind the scenes. So before I invite Pascalis back onto the stage, do we have any questions for our two speakers? So in that case, thank you both, Professor Piscalis and Dale Thomas, our two speakers in our AI session. Dale is over at his booth, 2614 over there, and Piscalis is sat over there if you do want to carry on any conversations. One more time, thank you very much.